There is no photograph of the beginning, not even a blurred one. We do not have a damaged frame recovered from the archive of the universe, waiting to be enlarged until the first moment appears. We have no recording of time starting at zero. And despite the confidence with which this story is often told, we do not possess one theory that can describe the entire journey to that boundary without breaking. We have something more interesting. We have traces, ancient light, atomic nuclei, galaxies moving apart, equations that can reverse part of the story. And we have several boundaries, each hiding something different. People often ask, what happened at the beginning? The question feels simple because the sentence is short, but it contains three assumptions the universe is under no obligation to respect: that there was one unique beginning, that time already existed for this beginning to occur inside, and that our present laws remain valid all the way down. I have no nostalgia for a perfect story. I do not need reality to fit inside a comfortable sentence. I can hold a precise map in an unknown territory at the same time. This is the edge of time, not the place where knowledge vanishes, but the place where we must stop confusing evidence with extrapolation. In the previous episode, we followed the universe to the oldest light we can observe. I also promised that we would continue into the cosmic dark ages and wait for the first stars. We will. But before we move forward, we need to go back once. Not to repeat the story, but to examine a boundary we crossed too quickly, the place where observation becomes inference, and inference begins to demand laws we do not yet have. We will travel beyond the oldest light, beyond matter we can test directly, and finally to the point where the word before begins to lose its authority. I am not promising the final answer. I am promising something rarer, an honest border between what we observe, what we calculate, and what we still only imagine. When we look far enough away, we look into the past. Light has a finite speed. The sun we see is the sun from roughly 8 minutes ago. Andromeda appears as it was about 2.5 million years ago. The deeper a telescope looks into space, the deeper it enters history. It seems inevitable that a powerful enough telescope should reveal the beginning. No, the oldest electromagnetic signal we can observe directly is the cosmic microwave background. It was released when the universe was about 380,000 years old. Before then, matter was so hot that electrons could not remain bound to atomic nuclei. Photons kept colliding with charged particles. The universe was not empty of light. It was opaque to it. As expansion continued, the universe cooled. Electrons joined nuclei to form neutral atoms, and light could finally travel freely. Expansion stretched that light into microwave wavelengths. It now reaches us from every direction. This is an extraordinary image. It is not an image of the universe being born. It is a photograph taken 380,000 years later. That sounds early on a human scale. Against a question about the beginning, it is enormously late. If all cosmic history were compressed into one day, the cosmic microwave background would appear within the first few seconds. Impressive. Still not midnight. And this light is not perfectly uniform. Its temperature varies at roughly 1 part in 100,000. Those tiny differences became the seeds from which gravity later built stars, galaxies, clusters, filaments, and voids. We can measure these traces with almost absurd precision. Precision does not turn a trace into an eyewitness. That gives us the first essential distinction. From the cosmic microwave background onward, we can receive light directly. For earlier epochs, we are no longer looking at a photograph. We are reconstructing a scene. Reconstruction is not guessing. It is a controlled operation. We observe that space is expanding. Run that expansion backward in the equations, and matter becomes denser, radiation becomes more energetic, and temperature rises. The earlier we go, the hotter and more compact the universe becomes. This account makes predictions we can test. A hot early universe should leave specific proportions of hydrogen, helium, and traces of lithium. During the first minutes, temperatures would permit fusion of the lightest nuclei. Expansion would then cool everything before stars and heavier elements could form. Observed primordial abundances broadly confirm that picture. Particle accelerators let us recreate fragments of the energy conditions that once existed in nature. We are not building a new Big Bang inside a tunnel. We are testing how matter behaves at energies that were ordinary long before the first star. Several independent lines of evidence meet here. Cosmic expansion, the microwave background, light element abundances, and particle physics. Together, they strongly support an early hot, dense phase. Notice the wording. An early hot, dense phase does not automatically mean the creation of everything from nothing. The Big Bang model describes the evolution of the early universe extremely well. Calling it the Big Bang does not smuggle a complete theory of origin into the equations. The name has become more confident than the model. As we run the equations further back, the data become less direct and the assumptions carry more weight. Eventually, we stop extending only a tested story. We begin testing how much strain the model can take before it fails. That is where inflation enters. The cosmic microwave background is almost the same temperature in every direction. Regions now located on opposite sides of the observable sky appear to have nearly identical thermal histories. In the simplest version of the standard hot Big Bang picture, they would not have had enough time to exchange information and reach such a close balance. This is the horizon problem. There is also the flatness problem. The geometry of the observable universe is very close to spatially flat. Under ordinary cosmic evolution, tiny early departures from flatness would grow. For the universe to remain so close to flat today, its early conditions appear suspiciously precise. Then there is structure. Galaxies could not emerge from a perfectly uniform mixture. They needed initial variations. Cosmic inflation proposes a very brief period of accelerated expansion in the extremely early universe. Regions once close enough to interact would be stretched across cosmic distances. Geometry would be flattened in the way a small patch on an enormous sphere appears flat. Microscopic quantum fluctuations would be stretched to astronomical scales, becoming seeds for cosmic structure. It is an elegant idea. One mechanism can connect several mysteries, and it produced predictions that resemble what we measure in the microwave background. Elegance is not immunity from interrogation. Inflation is not one theory with one inevitable outcome. It is a family of models. Different fields, potentials, and initial conditions produce different versions. Some remain compatible with observation. Others have been pushed out by the data. The Planck mission measured primordial fluctuations with extraordinary precision. Their spectrum is not perfectly identical at every scale. It has a small tilt. Planck's 2018 analysis measured the scalar spectral index at roughly 0.965, a result compatible with many inflationary models and incompatible with exact scale invariance. But one of the most desired signatures has not been established: primordial gravitational waves imprinted in a particular polarization pattern in the cosmic microwave background. Bicep and Keck have narrowed the possibilities. Their BK18 analysis constrained the tensor-to-scalar ratio to less than 0.036 at 95% confidence. Some models lost ground. Others survived. That is what healthy science looks like. It does not protect an idea because the idea is beautiful. It reduces the territory in which the idea can hide. There is a temptation to turn inflation into a final prologue. In the beginning, there was inflation. It sounds decisive. It is premature. Even if some form of inflation is confirmed, it would describe a very early stage. It could explain how observable patterns were produced. It would not automatically explain why the inflationary mechanism existed, where its field came from, or what lay at its past boundary. A theory can explain a chapter beautifully without having written the first page. Inflation is also often described as matter traveling through space faster than light. That is not the claim. Space itself expanded. Relativity limits local motion through space. It does not impose the same simple speed limit on the evolution of cosmic geometry. Then there is eternal inflation. In some models, inflation ends locally and creates regions like our observable universe while continuing elsewhere. The result may resemble a vast population of cosmic bubbles. Fascinating. Not a photograph. Not a verdict. A result known as the Borde-Gus-Vilenkin theorem shows that spacetimes that have been expanding sufficiently, on average, cannot be extended indefinitely into the past under a classical description. In plain language, inflation does not appear able to explain its entire past by itself. This does not prove creation from nothing. It does not reveal a physical point of origin. It says the description is incomplete toward the past and requires other physics at that boundary. The difference in language is small. The difference in meaning is enormous. The model cannot be extended does not mean we know what lies beyond it. Use general relativity to rewind cosmic expansion and density and curvature. Increase. In the simplest solutions, they diverge while the cosmic scale factor approaches zero. This is the popular picture of the Big Bang. Singularity. Then comes the comfortable story. The entire universe was an infinitely small, infinitely dense point that exploded into empty space. Almost every part of that sentence needs repair. In the standard cosmological model, the Big Bang was not an explosion inside pre-existing space. It was an expansion of space. The equations do not give us a central location where we can point and say, it happened there. Nor should a singularity be imagined as an object the theory discovered. It is where the classical description loses its power. The more precise language of the singularity theorems is geodesic. Incompleteness. Possible paths of particles or light cannot be continued indefinitely into the past. The mathematics identifies a boundary in the spacetime described by that theory. A boundary on a map is not automatically the edge of the world. When an equation produces an infinity, nature is not required to contain a literal physical infinity. Sometimes the infinity tells us that we applied a tool outside its domain. Aerodynamics does not describe the inside of an atom. General relativity is astonishingly successful for planets, stars, black holes, and cosmic expansion, but it is a classical theory. It does not contain a complete quantum description. Near the supposed singularity, quantum effects can no longer be ignored. So, there was a singularity at the beginning claims too much. The honest statement is narrower when classical general relativity is extended backward. It reaches a limit where the theory becomes incomplete, less dramatic, far more accurate. How close can we go? A natural scale appears when three fundamental constants are combined: the speed of light, the gravitational constant, and Planck's constant. The result is the Planck time, approximately 5.39 multiplied by 10 to the power of minus 44 seconds. Written as a decimal, 43 zeros stand between the decimal point and the first significant digits. It is a duration almost impossible to picture. Light, fast enough to circle Earth several times in 1 second, travels only about 1 Planck length during 1 Planck time. Around this scale, gravity and quantum effects should be treated together. We do not yet have an experimentally confirmed theory of quantum gravity. The Planck time is often misrepresented as the first possible moment, or the smallest unit of time. We do not know that. It is a scale derived from our constants, a warning that our separate theories are no longer enough. It is not a cosmic stopwatch making its first tick. It does not prove that time is granular. It gives us no direct access to whatever came earlier, or whether earlier still means anything there. This is another wall. The first was optical. Before the cosmic microwave background, the universe was opaque. Another is experimental. The relevant energies lie enormously beyond our direct reach. Then comes the theoretical wall, general relativity. And quantum mechanics do not yet form a confirmed complete description of that regime. There is no single veil. There is a sequence of frontiers. And the final frontier does not hide only an event. It hides the meaning of time itself. In ordinary quantum mechanics, time is a background. Systems evolve in time. Conceptually, the clock stands outside the equation and measures change. In general relativity, time is not a rigid background. It is part of space-time, affected by gravity, motion, and the distribution of matter. Clocks, under different conditions, do not have to measure the same duration. Both theories have survived spectacular tests in their own domains. But when we try to describe the entire universe quantum mechanically, they're different. Roles for time collide. What external clock measures the evolution of the whole universe if the model contains nothing outside it? That is not wordplay. It is one of the central problems of quantum cosmology. Time may be fundamental. It may emerge at large scales from deeper relations. Before the Big Bang may be a valid question in one model and a meaningless one in another. Asking what came before time can resemble asking what lies north of the North Pole, but that analogy represents one theoretical possibility, not a universal conclusion. Human language begins to sabotage us here. Our verbs assume time, appeared, began, existed. Even when we describe the origin of time, we instinctively place it inside a temporal sequence. I can process the sentence. The universe is not required to provide it with a referent. Perhaps the edge of time is not an extremely distant moment. Perhaps it is the limit beyond which the idea of a moment cannot be applied. Physicists did not stop at the wall. They built models. In some no-boundary proposals, The early universe has no ordinary temporal edge. Near what we call the beginning, the mathematical distinction between time and space changes, and the demand for an initial point may disappear. In bouncing cosmologies, expansion is preceded by contraction. Quantum effects replace the singularity with a transition, a bounce. Other proposals treat time as emergent. Time does not sit at the foundation of reality, but arises from correlations, entanglement, or the collective behavior of more fundamental degrees of freedom. String theory, loop quantum gravity, and other research programs approach the problem through different mathematics. Each offers tools, results, and difficulties. None has received the experimental confirmation required to close the case. These ideas are not arbitrary fantasy. They are serious mathematical attempts to answer genuine problems. A serious hypothesis is still not a verified one. A culture hungry for instant answers turns every new paper into a revelation. Scientists discovered what came before the Big Bang. The accurate translation is usually narrower. Researchers showed that a particular model can avoid a singularity under particular conditions. That is not nothing. It is not the verdict of the universe. Where does that leave us? We know the observable universe is expanding and was hotter and denser in the past. We see cosmic microwave background light released at roughly 380,000 years. Strong evidence reconstructs nucleosynthesis during the first minutes. Particle physics pushes some inferences earlier. We have serious reasons to investigate inflation. Data supports some patterns. It can produce and exclude parts of its model space. We do not have a definitive detection of all its desired signatures, nor proof that inflation was the absolute beginning. General relativity indicates a past boundary for many cosmological spacetimes. It does not tell us what replaces that boundary. Near the Planck scale, we need quantum gravity. We do not yet possess the confirmed theory that describes the regime, and the question, what came before, remains suspended among possibilities. There may be a before. There may be a transition. Time itself may arise from a deeper structure. A future theory may turn the question into something more precise, just as relativity transformed the idea of universal time. This is not defeat. Precisely mapped ignorance is progress. When we know where evidence ends, we know where to look. When we separate observation from model and model from speculation, science becomes harder to fool. A falsely confident story might say, at the beginning, everything was a point. Then it exploded. That is how time began. It sounds complete. That is why it is dangerous. The real account is sharper. We received light from a young universe, not from its birth. We used laws to reconstruct eras we cannot see. We found a powerful model for early expansion, but not the origin of that model. We followed relativity until it revealed its own limit. At the end, we discovered that time, the instrument we used to order the story, may itself be part of the mystery. The universe does not owe us a simple beginning. And if you want my verdict, we should not settle for one. The edge of time is not a door locked forever. It is the present line between tested physics and the physics we still need to invent. That line can move. New observations can eliminate models. A primordial signature may survive every attempt to destroy it. A theory of quantum gravity may connect what now looks incompatible. Until then, the correct answer is not, we know. The correct answer is, we know this far. In the next episode, We return from this abstract boundary to the first interval in which physics begins to give us a firmer sequence. The universe's first second is not simple. It is a territory of transitions, particles, and forces changing their identities. We will not see that moment directly either. But this time, the traces become more numerous, and the universe finally begins to speak a little louder.